Okay, everybody looking at my slides, Science Fair series. Let's get started. Okay, hi, welcome. I'm Sheila King from representing the NEO-STEM Alliance and the Akron Council of Engineering and Science Societies for this Science Fair series that we're working with the Summit County Public Library. Summit County Public Library, that's right. So I'm just going to get started. We had a couple videos up online for you to review about creating your hypothesis or your engineering design statement. And so I kind of wanted just to review those very quickly. And just a couple slides that you might have looked at just to help you remember. So there's two types of projects. There's the inquiry-based science project, which you're probably most familiar with hypothesis and conclusions. And then there's the engineering design project, which is an engineering design or innovation or maybe even a design improvement over a current design that's out there. And I just wanted to mention that these are parallel processes. So what you're familiar with, state a question, there's define a need. And this is all talked about in the videos that you can find from the library. And then there's also one about library research. Here's the link. And these slides will be given up to the Akron County Library to put these on their desk or on there. So the thing I wanted to mention, and you'll see this slide over and over again through this presentation, is how important it is to enter the information into your notebook log for your research. This is where you would start to put your content when you're doing your research from the library. You would put your date, your source, and your notes and comments from the library. And then I also have the video. Is that a question? I didn't hear that.
No, there.
Okay.
Once in a while, your voice gets a little muddled, but it seems to be okay.
Okay. So there's the videos that you probably saw already. I just have these links on here in creating a hypothesis. And then also, here's the link for that. So just to kind of review a little bit about the inquiry project, there's the scientific method where you state a question, do your background research, formulate a hypothesis and identify variables, design experiment and establish your procedure, test your hypothesis by doing the experiment, and then analyzing your results and drawing your conclusions. So just a quick review about that though. In order to create your hypothesis, you have to know what a cause and effect is, and it's something that we all know what it is. It's just kind of putting terminology to it or putting words to it. There's a cause that when there's two events that happen, there's a cause that causes the event, and then there's the event that happens. So why it happened or what happened, like if you kick the ball will roll, right? And so it's an important part of a hypothesis. And that whole cause effect thing is how you would create your hypothesis. If the cause or your independent variable, then your effect, which is your dependent variable, and the science principle that's being tested. Now, this is just a review of the slides, so go back and check the slides for more information on this. But I did also want to say, again, another important item, enter it into your notebook log for the Science Fair project, put in your hypothesis with the date, the hypothesis, and notes from the discussion with a scientist or teacher if you have one about your process. Real quick, the review about the engineering design process. The steps are define a need, do background research, establish design criteria, prepare preliminary designs, build and test a prototype, and then test and redesign as necessary. And then you would need to create your design statement, much like you had to create a hypothesis. And this is really important. And we're going to have a workshop, and we'll talk about it in a minute, about helping folks with their design statements and hypothesis so their project is successful. And again, here we go. And I said you'll see this a lot today. Notebook entry. So when you've written your design statement, get it in your lab notebook, put a date, your design statement that you wrote down, and notes from any discussions with scientists or teachers. So today, let's talk about the forms. Now, I want to talk about also the recommended schedule for a science fair. One thing that people make a big mistake in when it comes to science projects is put it off and put it off and put it off. And then they have so much to do at the very end and it's no fun. So you really need to stick with a recommended schedule like this. It makes it fun if you don't have too much to do in the period of time. So stick with this. Pick your project in September. Determine your project plan and your strategy in October. In the month of November, perform your experiment or build your prototype. In the month of December, perform your analysis and conclusions. And then in January, write your oral and written presentations. So before you begin, understand the policies and rules of Science Day, because all the science fairs around here are affiliated with the Ohio Academy of Science, and review the judging criteria. The rules for the science fair are ISEF rules, or and these are the standard for undergraduate research. You need to understand the policies and the rules, and I have on here the link to the Ohio Academy of Day Standards, and just an image of what that website looks like. And review the judging criteria. We talked about this at the very beginning, or the very first one that we had, and I wanted to show you where you can get a copy of the scorecards, because it's important to know how they're going to score you. So there's individual scorecards for your engineering design or science inquiry, and the same for team projects, okay? So now you're going to create your project plan. Forms first for safety. So you can get your forms from this link right here, NeoSTEM forms. We have all the forms there if you need them. I'll show you real quick, right? So you go to how to create a project plan. Here's all the forms. And we'll discuss those forms in just a sec. But these forms are mandatory for moving on to the district and state science fair, which we're hoping that you'll do. We hope that you're successful and you move on to the science fair. So get the forms. And then there's another flip for you, because the form just tells you what information to put in there. And we have a template that you can download from this site. So here we go again, notebook entry plan for forms. What forms do I need and who needs to sign the forms? So again, if you go to the website here, you can see there's checklist for adult sponsor is mandatory for all forms. And this is something that your parent or your teacher would fill out. So that, let me hop over to that form. So that, so it's a checklist for adult sponsors, and it basically is a checklist for safety, right? So you say, do you have any humans or vertebrates or potentially dangerous biological or some microorganisms? You can check these and they'll help you figure out what forms you need, right? So this is what your parent will fill out so that they can do a risk assessment. And these things are important to do prior to your project. This is the research plan template that I was talking about. And this is something you can download again with the links you can get to about the research plan. And these are important things to do because this is a form that you'll need in order to compete at the district. You need your rationale, what's your research question or your engineering hypothesis design statement, your goals and expected outcomes, and the methodology, just what your procedures are, any risk and safety. So if you have, you know, if you need gloves or if you need just what kind of risk and safety you would need, and then how you're going to analyze your data, how you're going to decide that your project's been successful. The rest, and then a bibliography. These are all things that you need to report in your research plan, and these other things are just considerations for the other forms like I was talking about. Just real quick, if you go back to here, there's 3 forms that are mandatory. The student checklist is basically your name and information, and then the research plan that I just went through. And then the approval plan is just your parents and your teachers approving. So these are your 3 mandatory forms. You only need to fill out those 3 forms unless you have other issues like humans that are in your project, or that you have hazardous chemicals or biological agents. And just to mention something real quick, anytime you have a Petri dish that that is basically now considered a potentially hazardous biological. So make sure you understand the rules. Okay, if you get the rules up front, then it makes it easy after that. Okay, so then your plan for forms. So now we can move on. Now we've got their plan, forms, and so we're nice and safe. And now we can go on to our projects, right? So in engineering design, what's after your design statement, right? So now you have to create your preliminary drawings, sketch your drawings, and you can create flow diagrams if it's a software project, and make a material list. And then again, this is a slide that we'll see over and over again, because it's really important to get all this information into your notebook, engineering notebook for an engineering design, or your science project. So here, put your sketches in your design, the name of the preliminary design, like design A or design with wings or design, name it, the description of the design and the version, right? Because you will change your versions. Prepare an assembly procedure. So when you have a design, the first thing you have to be able to do is to build it. And what's important about that is you have to list the steps in detail of how you're going to build it in such a way so that if somebody else were going to build it, they could follow your instructions. So if they followed your instructions, they would come up at the end with the same thing. Assembly instructions for your preliminary designs. Name of the design, right? Put it in your notebook. The name of the preliminary design, and the assembly steps to build. Make sure you get it all in your design notebooks or in your lab notebooks. Now you have to develop a test, because in an engineering project, what you're doing is you're saying, I'm going to create something that goes faster than the current thing, or that's better than the current thing, or a brand new thing that does all these things. And so you have to be able to show that you created that and test that you created it. So at the end, you have to test it and say, is it faster than, like you said, you're going to invent something that was faster, better, right? Or something completely brand new that does all these things. Does it do those things? So you have to create a test plan. And some of the test plan may just be human summaries. They tried it and it worked for them or whatever. And again, notebook entry, put your test plan in there, the name or the date, the name of the design that you're testing, and the preliminary tests, again, and the version of that test. Okay? So you've created your design, you've created your assembly procedure, you've created your test plan, and now, so when I say created your plan, you create your paper plan, create your assembled instructions, and create your test plan, and now you're actually going to assemble it. So you're going to use your own assembly procedure to build it, and then also take notes to improve the design. So when I say take notes to improve the design, what do you think the next slide is going to be? A notebook entry, assembly notes, date, the name of the design, the tests for the design or the version, assembly instructions used for the assembly, and notes on the instructions, changes needed, like do this thing first. Because sometimes when you're building something, you build it out of order and you have to take it apart and change the order. So make sure you make those notes. And then you run your tests. You test to determine if you've met your design criteria. Okay, and so here you have a little notebook entry for your design tests. Name, test name, variable under test like the speed or whatever it is that you said that your criteria can do, test notes, and observation or anything you notice. And now you'll analyze it. You'll say you made your tests, and then you're examining your data, and you'll say, okay, now that I've done my tests, did I meet my design criteria, or do I need to improve it? So quite often you need to improve it, make another tweak or something. So here's your evaluation, your notebook entry. You're saying, okay, here's the name of my design, the summary of my tests, the evaluation if it met the criteria, yes or no, and changes that you need to make to if you aren't meeting the designs, or if you thought, when you put it together, you're like, no, if I did it like this, I would make it just a little bit better. So again, notebook entry, note to notebook. So then you'll write your description of changes and refinements, issues to be addressed, description of changes, and then the reevaluation of the design after your tests. Okay, and then after that, we'll get to where we're talking about data. And so you'll want to watch the data series that we have. So let's go over the process for a scientific inquiry project real quick. So we've talked about creating your variables, your cause and effect, and the variables that change, independent variable, and your dependent variable being the one that you measure. The independent variable is the one that is changed by the scientists. The dependent variable is the one that responds to the change. So if the temperature cools, then the water does not dissolve as much sugar, right? So that's your dependent variable. And then your controlled variables are all those other quantities that are kept constant. So note to notebook, you have to write down the specification of your variables. Write the date, the independent variable, and the units of measure, the dependent variable, units of measure, and how you're going to measure it, and the controlled variables, and your plan to keep them, all your controlled variables controlled. Okay, so now you have your variables, and so let's design our experiment. So the first step of designing your experiment procedure involves planning how you will change your variable and how you'll measure its impact, right? So it's just very simple of what we were doing. And it's important to understand what a fair test is. And that means that you only change one variable at a time, and that way you can see how that change affects your system. And the only way you can say scientifically that a change makes the change in one variable and your independent variable results in a change to your dependent variable. The only way you can do that is if you keep everything else constant, and that is the definition of a fair test. And it's important that you mention that when you talk to your scientists for your project. Notebook entry, plan to validate hypothesis, right? So how you're going to do it, log your journal entry on brainstorming for how to validate your hypothesis, right? And this is, again, making sure that everything you think, everything you do about your project gets in your data log. It's so important. So you're going to write out your procedure, and writing out your procedure is much like writing out your assembly instruction for an engineering design. A good procedure is detailed and complete that somebody else can duplicate your experiment exactly. So you have to do that. So here's an important part, number of repetitions. Repeating a science experiment is important to verify your steps. So typically, you should plan to repeat at least 3 to 5 times. Actually, statistics, if you're going to be doing statistics, or if you're going to move on to district or regional fairs, you should consider a repetition of up to 15. So if you're going to do something, you should, some quick tests like what happens at this temperature, what happens at this temperature. You should plan to do that around 10 to 15 times so that your data is good. When you're doing something like growing plants, you should do the project experiment with at least 3 plants in separate pots. That's the same as doing the experiment 3 times, right? Notebook entry, write out your procedure. The date, procedure, notes from the discussion with the scientist or teacher. Now, you've created your project and you've written down your procedure. Now it's time to execute the procedure. And what's really important is collecting the data. It has to be accurate. It has to be precise. It has to be clean. And when I say noisy, that means you don't say, oh, that's about 2 1/4 inches, or that's about so many grams. Make sure that you have real good data, and then when you do, then you'll be able to see variance and outliers, and those are important things to talk about when we get to our data. So here's our notebook entry, test data log. So when you have your tests, you'll write down your independent variable, the dependent variable, controlled variables, process notes. Now, if you make a mistake, like if you add too much of something, when you have, say, you have to only add so much, and you make a note of it. Don't pretend that it didn't happen, because it's going to change your outcome, and that you're going to need to understand that. So make any notes to confirm that you controlled your variables. So if your temperature of the room is a controlled variable and it gets out of control, make a note. And observations, things that anything that you notice. So like if you are looking at growing petri dishes of stuff and then you see something on the side that seems completely independent of your project, make an observation, right? So write everything down. It's very important to log your data. It tells the story of your science project. So now that you've done your tests, you'll do an analysis of the tests and enter this into your project. So the date, the summary of the tests, and the conclusion. So you're looking at your data, and we'll talk about this in the data clinic that's scheduled in November, I think. And then here's the thing, thoughts on repetition. So if something didn't go exactly right, you might say, you know, maybe I need to repeat some part of that experiment in order to clarify my results. And you should think about that if you want to make sure that if something went wrong and you're like, you know, that wasn't what I was expecting, maybe I should do it again. And my daughter did that with her, she had an algae project and she was the results that she didn't think was right. She did it again and the results were the same. So you're like, okay, well, I guess she did do it right. So again, here we go, notebook entry, repeated test summary, the dates of the test, conclusions, and did the results validate or invalidate your hypothesis? So, okay, so now we've done our projects. What's the next steps of what our project plan is? So we want you to write your hypothesis and engineering design statement. And then we have a hypothesis or engineering design statement workshop where we're going to, you can submit your hypothesis or your engineering design, and then scientists in a panel can give you some recommendations on the safety of your project. Say, hey, make sure you think about this to make sure it's safe, or we can talk about how to make it, change it up, or some different recommendations if we think that if you choose it is successful. So you can so write your hypothesis, engineering design statement, and submit it to the library email, and I have that on this stack, and I'll show that to you in a minute. Your submissions can be anonymous, and attendees can ask questions in the panel discussion. So that's the hypothesis and engineering design statement. That is on October 8th, 9th, or 10th from 4 to 5 p.m. The next thing is your project plan, and this is where scientists can discuss your hypothesis or your design statement to help you improve it or make any recommendations or tell you that it's great if it's just great. Develop your project plan. Now this is the research plan, and this is just to check to make sure that your procedure is good, and you can submit your project plan for recommendations and discussion with the science panel. So up here I showed you earlier in a few slides, I showed you the research plan and where you can download that. And again, those submissions, they can be anonymous to the library, and we'll just discuss it and everybody can learn from it. And attendees can ask questions in the panel discussion. So that's the next thing. Develop your hypothesis or your engineering design statement, attend the workshop, and then develop your project plan and attend that workshop on one of those days. Here's the library email. Submit your hypothesis, design statement, and research plans to this library email, and we will have them and review them beforehand, and we'll talk about it. Okay, another thing, I have the NeoSTEM Alliance website here for more project information, and then which is again here where you can get the forms, the slide stacks from before, or other items are on this page, so you can download stuff. And then of course the scorecards are in here also. And then the slide stack will go up here on the library website. So, and that's the presentation. And now we have time to answer any questions.
I have a question.
Sure.
So you talked about petri dishes.
Yes. Mm-hmm.
Okay, so for one of my ideas for my science fair experiment was it was about the 5-second rule and how well it works. So me and my mom we're gonna do a test a project this weekend. So we're gonna take bread and drop it on different surfaces. And then, like with a petri dish or something, see how much bacteria it picked up. Would that be a good science fair experiment? Or like,
So,
do you know what would be best so that we could find something to help us view the bacteria easier?
so yeah, that might be, and that would be something where you would have to have a whole bunch of bread. You'd have to label them, right? So if you were going to drop them in the dirt, you're going to drop them on your kitchen floor, and then on your bathroom floor, and then maybe a project where you're, seeing different times. So say if you drop bread on the floor, or so you can see that there's two separate types of experiments there, right? One where you're seeing how long it might take for bread to pick something up, or another thing is different places that you can test. So what I would do, you wouldn't necessarily need a petri dish. I would, just get plastic bags and drop it on the ground, and then count your time and put it on your. If you're going to lay them all out, you have to lay them in a place where they all get the same amount of light. They have to all, so you have to have a nice place where they can, all the other variables are the same for everything. And then you can label it and then measure it in a week, measure it in 2 weeks, and see if there's a difference between what grows on your bread.
Okay.
So you wouldn't need a microscope for that, because you're going to give it plenty of time to grow.
Oh, okay.
Right. So different things that grow, if they are growing, they're going to grow bigger and bigger. Yeah. So, and of course, again, another thing about keeping everything the same is you have to use all the same type of bread, right? So you can't use wheat bread for some of it and potato bread for other ones, right? And so when it comes to doing the project, you might do a little research, so what grows on bread? And maybe what different types of bread? Maybe potato bread has more sugar in it, and so it makes it so that something grows on it faster. Or maybe, wheat bread doesn't, and so some things don't grow on that faster. So do a little research about not only what you're trying, where you think your germs are, right? And what they might need to grow, and then I would try that. It sounds like a fun experiment. How old are you, Jocelyn?
I'm 12.
What grade is that? I can't remember. Is that 7th grade?
It is.
Oh, great. All right. Well, cool. Yes. Well, you should have it. It'll be a fun experiment. And, and do the kinds of things of, do some research. You have to have some scientific understanding of the things that you think you might pick up, right? So what's growing on your bathroom floor? What's growing on your kitchen floor?
Right.
So do some research and kind of find out in advance of what you might be looking for and how you might find it.
Okay, thank you. I have one more question.
Sure.
Okay, so I like elephant toothpaste. I've made it before, and my mom told me it's not really a project, it's more of an experiment. But I was wondering, like, what if I changed something? Like, what if I would see, like, different peroxides? Because there's different volumes in peroxide. So I was thinking, like, for my science fair project, could it be like, which value of peroxide makes the elephant toothpaste either explode faster, or I wasn't really sure if I could do that with anything, with it being like an experiment.
So why don't you tell me what elephant toothpaste is?
It's like where when you so you take dish washing liquid, and then you mix in some peroxide, and then you mix your yeast with water, and then you add it in, and you mix all of that into the bottle, and then it shoots up in different colors if you add food coloring to it. So here,
So yeah, so that's what I would consider a demonstration,
okay,
right? It's not really a science project. So a science
right,
project, you have to change a variable, right?
right,
So you might try to find, but you can do something like that where you say, how can I create more foam? How can I make the explosion happen faster or
okay,
last longer, right? So you have to change something and then measure something else, right? So if you say,
right,
my goal is to for 10 minutes, right? Right. So you would
right,
figure out what you needed to add, and then you would add stuff to your, and I don't know anything about elephant toothpaste, so I'm just sort of winging it here, but you would change some variables, change a
right,
variable and measure the change that it makes in your, the content of the explosion, right? Or the contents of foam that it makes.
right.
And
So
then
I
you
was
would,
thinking if I was to change like the volume of peroxide, does the different volumes of the peroxide determine how fast the elephant toothpaste explodes out of the bottle? Because the yeast, after you add the dishwashing liquid and the peroxide, and then you add your yeast that you mixed with your water, the yeast is what makes it help explode it because of how it mixes with the peroxide. So I wasn't sure if that would work or not.
yeah, so that would be where you're changing the amount. I'm sorry, Michelle, were you going to add in? Um,
I was just going to say that what she's talking about right there is a question that becomes the question, and you can use some research to help make a hypothesis that the amount of peroxide will increase the length of time that the toothpaste, that the chemical reaction continues, or the amount of yeast that you put in. So each one of those amounts is then going to become one of your variables. And you just need to decide, which one you want to change, which one you're not going to change. How are you going to measure all of those things? So yeah, that's all. I was just going, yeah, that's exactly right.
yeah, yeah.
Okay.
Hi.
Hi.
The other thing I did want to mention is the kinds of research that Sheila was talking about. Those are things that you can contact the library and use some of the resources that I talked about in that video to start doing some research on that to find out more about all of those things that you're considering, both for the bread experiment and for the elephant toothpaste experiment. That's awesome.
Yeah, and also and remember, I don't know if you heard our first presentation, but when it comes to the 4 things you get judged on at the science fair, one of them is the content, your knowledge achieved, which is what they're called. So what would be important in the elephant toothpaste, like when I mentioned the bread one, how you would research what is out there and what is in the bread that would make something grow, and so you would also need to understand, if you were doing the elephant toothpaste, you would need to understand the chemical reaction that happens, how acid and base is, what's the deal with the yeast, right? How does that, and it creating oxygen, and is sugar, there's probably sugar involved and stuff like that. So you would have to understand the science of the chemistry of the reaction that you're trying to manipulate, right? That would be very important for a successful project, is to be able to understand what the different variables in the, what the yeast does, what what'd you say, the hydrogen peroxide, is that what peroxide is, and what all these different things are, sugars, there's probably other things, how they will affect the chemistry and what the chemistry is. And it would be really important to learn that and to be able to explain that.
I'm going to chime in again. That science project index that's on the library's website that I mentioned, that actually, you could look up elephant toothpaste in there, And many of those experiment books do talk about what's happening in this experiment. So those would be another really good place to start looking for those kinds of explanations.
Okay.
That sounds great.
Yeah.
Any other questions? You have your science notebook, your notebook?
I do have one.
Good. All right. Important to keep one.
Excellent.
Did you want to see an elephant toothpaste explosion so you know what I mean?
Sure.
Okay.
I think I'm going to need to make you a co-host in order to let you share your screen. So I'm doing that right now.
Okay.
Okay. So now you should be able to share your screen on the bottom of your, do you see a little share screen window or a little share screen button?
I am looking for it.
It should be right across the bottom. And you may have to move your mouse over it to actually see them.
I do.
There you go. Because they disappear when you're not hovering on them.
Okay.
And that will let you share a window from like your browser or something else on your computer.
Okay. Give me 1 second.
You're fine.
Can you see it?
Mm-hmm. Yes.
Wow.
That's awesome.
Yeah. Yeah, see where it says safety? That's where you would have to fill out your forms and say what you're doing to keep yourself safe.
Okay.
So you'll have to fill out your risk assessment. That's pretty cool. You have to help, but you can't help but wonder, as you're looking at these kinds of things, um, you might also just, wow, that one shot up in the air.
And you notice that in the description there, it talked about the different amounts of hydrogen peroxide. So that might be a clue to you about some of the variables that you need to be aware of.
Right.
Yeah. Huh. So that one's in the bigger one. Add dish soap, huh? So this is another thing where different things you can try, but you have to understand the science. Okay, so this is where they have
The stripes.
stripes. Huh, that's so pretty. So that's the one with the soap with all the bubbles. Huh?
Mm-hmm.
Your reaction produces heat. See, that's one of those things where you would need to understand the science. 40 volume. Oh my gosh, so this is going to be a gigantic one, huh? Oh. Oh. Everybody does their own. Well, that's pretty cool.
Pretty neat.
Yeah. That's cool. So what's, again, what's important is understanding the science and having a variable that's changing so that you can have a hypothesis. Right?
Super.
And of course, when
Okay.
you have your hypothesis and you change something, you're going to say, I'm going to change this variable and it's going to have this effect. And this is where the science is important because why? Right? Because the chemical reaction, blah, 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 blah. Right? So, yeah.
Very
I
good.
look forward to seeing your hypothesis
Thank you.
in 2 weeks. We have any other questions?
No, I don't.
Excellent. Well, thank you so much for sharing your ideas and stuff with us. That's excellent.
You're
All right.
welcome.
It was a
So-
pleasure working with you, Jocelyn.
Thank you. You too.
We'll be sending out the slides from today, like we did last time, and posting stuff. And we hope that you'll join us for the next session.
Okay.
Awesome. All right. Bye. Have a great afternoon.
Bye.
Bye.
Thank you. You too. You guys too.